On the first page of this assignment, we're looking at the net change theorem and several applications of integrals. And then on the second page, we're looking more at the graphical relationship of derivatives and integrals. So in questions 1 through 12, the function that's given is already a rate. So this function, and I think you'll want to put that in your calculator to use throughout problems 1 through 12, that's the rate of change in the number of books available at the library. So the rate of change in books per hour. So notice that this is already a rate of change. It is not the number of books in the library, it is the rate of change. So I made a graph here. We're interested in hours 0 through 12. So I like to see the axis. So I set my domain of my calculator from -1 to 12. And then I use the zoom fit feature to let my calculator choose a good range. And then I went back in and just turned them into round numbers, is how I came up with the -200 to 600. You didn't have to make a graph, but it helps me to understand that what's happening at first here, when the rate of change is negative, that means the rate of change of the number of books available in the library is negative. And then when the function r is positive, that's the rate of change in books per hour of the number of books available at the library. So sometimes more books are coming in, sometimes more books are going out. And then another important piece of information you always want to look for is there an initial value? So at t equals 0, there were already 20,000 books in the library. So we'll make use of that where appropriate. All right, so read very carefully. So we're given a rate, and in question 1, we want the net change from hours 1 through 6. So when we integrate a rate, we get a net change. So this is very simply doing the integral of the rate, and you could calculate that, simply plug it in and round it off. And I don't know why we want thousandths of a book, but we weren't told to round to the nearest book, so I'm going to stick with my rules to the nearest thousandth. And this would be in books. Remember, when you do the area under the curve, you're going to be doing the product of your units. So books per hour times hour gives us the number of books. So that's the net change in the number of books in the library over hours 1 through 6. Number 7 is the total change. So remember, sometimes our rate is negative, sometimes our rate is positive. So the total change, so we're interested in the number of books coming in and out. So if we integrate the absolute value, and again on your TI-89, you can find that under the math menu, or you can find it at the top of the catalog, or you can type the letters ABS. But you can check that you come up with this answer. Question 3, write and evaluate a statement for the number of books in the library at hour 3. So here is where we need our initial value. We started out with 20,000 books, and then we want to add the net change over 3 hours. So after the third hour, we want to go from 0 to 1, sorry. Up above we were doing 1 through 6. Now we're doing from the start of the day, from 0 to 3. And I have in my notes 19836.056 books. If I happen to write a number wrong here, you guys can check your calculators. All right, in question 4, what is r of 2.5? So simply in your home screen, do y1 of 2.5, and I have approximately 96.472. And what is that? Our rate is given in books per hour. So what that means is the rate of change. This is the rate of change in books available at the library. At 2.5 hours. All right, so question 5 is our prime of 2.5. So you could let your calculator do the work there. So our prime, you want to do your derivative evaluated at 2.5. So find your derivative function, and we want to put 2.5 in. And I have, from my calculator, 202.303. And that would be the rate of the rate. So our rate, our R function was in books per hour. And now this would be per hour. Books per hour per hour. So what does this tell us? This is the rate of change in the rate. So the rate of change of the rate of books available at our 2.5. And because it's positive, notice another way of saying that would be to say the rate of change of books available is increasing, since it's positive, at 202.303 books per hour at t equals 2.5 hours. So I think both of those, hopefully I've written them as synonyms. All right, let's see what we've got next. Show all work to find the average rate of change. So we've got a rate function. So this is function r of t. So to find the average value of a function, we would use our average value formula here. So 1 over b minus a times the integral of the function. So that's the average value of r of t. And when I calculate, I have 34.601 books per hour. So that's the average rate at which the number of available books in the library over the first 4 hours. So that's the average of that rate. All right, in question 7, write a new function b of x that gives the number of books in the library. Well, that's similar to one we did up above. So we have to take our initial number of books in the library, and then we would have to add on our net change. And we want it to be our x starting at 0. So 0 to x of our r of t dt function. So it's our net change added on to our initial value. So b of x would give us the number of books available at any time. All right, so this would be in books. Show the average number of books. So now once we have a b of x function, now we want the average number. So we want the average value of b of x over our 0 through 4. So it's what we did up above, but this time we're doing the average value of our b of x function. And we only needed to write an expression, so I think I'm good there. All right, and then question 9. Now I've given you again the formula for b of x in case we might have had an error. So that is what we came up with in number 7, so we're looking good. Now we want to find the value of b of 6 and explain its meaning. So when we put 6 in, and again, you're going to use your calculator to evaluate this. We put 6 in for x, and then this would be our integral of our y1 function in our calculator. And I have 21,200 books. Available in the library at t equals 6 hours. All right, question 10. Again, let's use our b of x function, and this time let's find b prime. So b prime, the derivative of the 20,000 would be 0. And here we have the derivative of an integral. So remember that the derivative undoes the integral. So here's our fundamental theorem. So we'd get right back to r of t, except we have to remember to replace that upper limit with x. We don't care about the derivative at 0 because the derivative at any constant would be 0. So what happened there? So b prime of x is the rate of change in the number of books available. And as expected, which is equal to r of t, which was given to us at the start of the problem. So we came full circle right back to the change in the books available is our r of t function, which was given. Let's make that a sentence there. Question 11, use our b of x function to find the value of b of 6 minus b of 0. Remember, b of x is the books available, so b of 6 is the number of books available at hour 6. b of 0 is the books available at hour 0. So the numerator, and you can use your calculator to find this. So our b of 6 function minus our b of 0 function divided by 6. I have 21,200, which we've worked on, minus 20,000 that we know were in the library at time 0. So we come up with 200 books per hour. All right, so remember that our b function was the number of books available. So b prime, this is the rate, this is the average rate, sorry. So when we do the slope of a secant, we want to get the word average in there. This is the average rate of change in books. I'm just going to extend over here in the library over t equals 0 to t equals 6 hours. All right, so whenever you're doing the slope of a secant, make sure you get the term average rate into your answer. All right, question 12, write an equation involving an integral that could be used to find the time when there are 21,000 books in the library. So our b of x function was the number of books in the library. So we simply need to set that equal to 21,000. So our b of x function, we've got it many places there, 20,000 plus the integral from 0 to x of r of t dt is equal to 21,000. And you could use your calculator to actually solve, and we don't have to do that. We just needed to set it up. All right, now we're working with a geometric graph here. And we're doing relationships between derivatives and integrals. So if this is the function of f prime of x, that I think is not meant to be a superscript there, f prime of x, for some differentiable function f, over what intervals is f increasing? So if this is the derivative, then these are the slopes. So f is increasing. Always justify now. F is increasing where f prime of x is greater than 0. And that would be on the interval from -4 to -1. Oh, I'm sorry. I just read the question right in front of me. The question is decreasing. Let me erase that. All right. So change my mind here. The question says, when is f decreasing? F is decreasing where f prime of x is less than 0. All right, so that would be between 0 and 1. So that would be from, let's try that again, from -1 to +1 and from 1 to 3. And now let's think about what's happening here. The function is decreasing. It hits a slope of 0 and then it decreases again. Decreasing, hits a slope of 0 and then decreases some more. So what's really happening here at 0? It temporarily has a horizontal tangent, but the function is still decreasing. So this is a case where we would want to include that endpoint. So if you wanted to write them separately, I would make sure that I use closed brackets here. Or, of course, you could say, well, in that case, it's decreasing all the way from -1 to 3. All right, so the important idea is that decreasing hits a slope of 0 and then decreases some more. So this is decreasing all the way from -1 over to +3. So we need to make sure that we include this 0 point in our answer. All right, let's see. Question 14. F prime is what's given in our graph, and we want to know where f is concave down. So f is concave down. And of course, our first thought is when f double prime is negative, but we're not given f double prime. So let's think about when would f double prime be negative? When f prime of x is decreasing. That's when f double prime would be negative. And where does that happen? That would happen from -2 to 0. And now we got to think differently. Now what happens at 0? Would it be concave down? Not at an inflection point. So now we don't want to include. So that would be, that would be from -2 to 0. And then it's decreasing again. It is decreasing again from 1 to -3. All right, so make sure we don't include the endpoints there. If the graph is f prime, at what x coordinates does f have an inflection point? All right, so from the first derivative, so f has an inflection point. And again, our first thought is when f double prime changes signs. So when does that happen? When f prime of x changes from increasing to decreasing. And let's look at the graph and see where that happens. The graph changes from increasing to decreasing at -2 and at 1. And also when f prime changes from decreasing to increasing. And where does that happen? I think just at x equals 0. I think that should do it for that one. All right, now we want to evaluate the area from -2 to 0. So let's use our geometry. From -2 to 0, we would have this triangular region. So that triangle has a base of 1 and a height of 3. So 1/2 of 1 times 3. So that triangle has an area of 3/2. And then the quadrant, each quadrant of this circle has a radius of 1. This is below the axis. Let me get rid of some of my other arrows there. So this would be 1/4 of pi r squared, but r is 1. So this would be a 3/2 minus pi over 4. All right. And then we want to find the area from 3 to 1. So that would be equivalent to doing the opposite of the area from 1 to 3. So whichever you prefer, you just have to make sure you're thinking about negatives and double negatives. So we're doing the area from 1 to 3. And then that. And now this really doesn't look drawn to scale here. Our height is -1, or this leg, the vertical leg is -1, the horizontal leg is 2. So I'm not sure that looks like it's drawn to scale, but this triangle would be 1/2 of 2 times -1, or -1. And we're going in the opposite, so it's a negative area, but we're also going from right to left below the axis. So it's the opposite of -1 would be back to a +1. Did I think that through correctly? A negative times a negative should be a +1. All right, and then in question 18, now we're assigning this g of x function is going to accumulate. I'm going to write up here where I have some more room. So g of x is accumulating, accumulates the area under function f of t. So as we go from 1 to t, so remember that our sweeping starts at 1 and goes to t. So first, to understand this, we're doing g of 2. So we are doing the area from 1 to 2 of our f of t function. And have we already done that? Let's take a look. Our area from 1 to 2. No, we did our area from 1 to 3. Well, that's going to mean I'm going to erase this. That's interesting. If we're doing the area just from 1 to 2, is it just this blue triangle? So this would have only half that distance. So this leg would be 1 and that leg would be -1/2. So our triangle would be 1/2 of the base times the height. So we would have a -1/4, I think. So you can catch me. Sorry, I keep hitting other parts of my keyboard here. And then we want to find g of -2. So now we're integrating from 1 to -2. And again, if you wish, you can leave it this way, or you could, if you want to, change the direction from -2 to 1. But don't do both. So we got to think about the negative areas. If we're sweeping from right to left, we have negative areas. And if it's below the axis, we have negative areas. So sometimes we'll have double negatives. So we want to go from -2 to +1. So let's see geometrically from -2 over to +1. So I think we want that triangle and the entire semicircle from -2 over to +1. So we already did our 3/2, and now this semicircle is 1/2 of pi r squared with a radius of 1. So we would have 3/2 minus pi over 2. But we're sweeping, this negative is because we're sweeping from right to left instead. So we could distribute that negative sign. So we could turn it around, or we could leave it in this same order, but change signs. I think that looks pretty good. All right, and now we're doing something more interesting. Now in the next problem, we're going to do the derivative of an accumulator. So if function g is equal to an integral, then when we do the derivative of g prime, when we undo the integral, this is our FTC, our fundamental theorem of calculus. So, oops, that is a typo. That should be an X up there. These should all be X's on your paper. Sorry about that. All right, so now we're going to get f of x. So when you do the derivative of an accumulator function, we get right back to the integrand. That was our fundamental theorem. We undo the integral. So now when we want to find g prime of -3, we write that it is equivalent to f of -3. And just look at your graph. F of -3 is right in the middle of that section. Maybe we better look at it. F of -3 is this point right here. So it is halfway between 1 and 3. So this point would have a y coordinate of 2. I think that looks good. And then we want to do g double prime. Maybe we need to do some writing first. Let me switch colors here, and underneath here, what's the derivative of a derivative? So we're doing the derivative of g prime would be f single prime. So to find g double prime of -3, that would be equivalent to f single prime of -3. And so now we're going to read the slope from the graph. So read rise over run. So let's go back up to -3 and take a look. At -3, the slope right here. So look at what was happening. We were going up 2 units and over 2 units. So our slope is +1 right here. Our slope is equal to 1. So that's our derivative value. And we're getting there. Question 20 says, find the x-coordinates at which g has a horizontal tangent. So we could write, as always, that g of x has a horizontal tangent when g prime of x, which is equal to f of x, is equal to 0. So we can look at our graph and find out where is our f of x graph equal to 0, and that is at x equals -1, and when x is equal to +1. Oh, and then it says explain whether g has a local max or min. So again, I used up too much of our space. All right, so let's look and see what's happening at -1. And again, I'm going to clean up all of my notes on the graph here. So what is happening at -1 is that our graph is changing from positive to negative. And at +1, it's doing neither change. It has a bounce point. It hits the axis, but it doesn't change signs. So we're going to write 2 different answers. At -1, our graph changes from positive to negative. So let's get that into our answer. So at x equals -1, g prime of x, which is equal to f of x, changes from negative, other way around, positive to negative. So g of x has a local max at x equals positive 1. G prime of x equals f of x is equal to 0, but does not change sign. So there is no extremum. All right. One more. Given the graph above is f of x, and a new function g of x is x cubed, and yet a new function h of x is the composite of those, find h prime of 2. So for good measure, we have to do a chain rule. So the derivative of a composite function is the derivative of the outer function, leave the inner function alone, times the chain rule on the inner function. So we want h prime of 2 to be equal to g prime of f of 2 times f prime of 2. And we're going to read those from our graph. So the graph above is f of x. So we want to read f of 2, and we want to read f prime of 2. So let's go back to our graph and get those. So at 2. So now we are looking right here. So at 2, our y-coordinate appears to be negative 1/2. And right here, the slope, we are going down 1 unit over 2 units. So our rise is negative 1, but our run is 2. So the slope right there, I'm looking at this triangle. So the rise was negative 1, but the run was equal to 2. So we want a y-coordinate of negative 1/2 and a slope of negative 1/2. By coincidence, they are equal. All right, so this is negative 1/2. And our slope was negative 1/2. All right, so now we have to find out what g prime of negative 1/2 is equal to. So what is g prime? G prime would be 3x squared. So g prime at negative 1/2 would be 3 times 1/4. So now we have a negative 3/4. Oops, is it negative? I think it is positive. Sorry. Times a negative 1/2. So negative 3/8. That doesn't sound familiar. But I don't see an arithmetic mistake. So I'm thinking that looks pretty good. If you find my mistake anywhere, you can tell me about it.